right. Good morning, everyone. So, um, today we will be looking at the optics. So, this is what I have for the plan here. So let me pull up this PowerPoint slide here. All right. So a few reminders here. 11 homework number 11 is due on Monday. Okay. So if you haven't started, make sure you start it. You may be able to finish it over the weekend. Again, another reminder is final exam is scheduled on Wednesday. This is the early time, 7:50 a.m. So you probably want to set an alarm on this one. So I probably will send you guys the exam at 7:30 like usual. And then you are going to submit this Moodle again. Okay. So most of you guys were able to do that, submit on Moodle. Okay, so if you would still have difficulty, you can send your file in email to me. Okay, preferably in PDF file. Okay. Also, end of class survey. If you haven't done that, about 60% of you guys have done that, but there's still a few guys of you haven't done it. Okay, so make sure you do that. You will not lose Moodle access this time because we are having had to transit online, so there might be some difficulty for some people. So the schools decide not to take your access to Moodle away this time, but I will still encourage you guys to do that because as current situation stands, there's not like there's still chances that we might not be able to get back to campus next semester, but hopefully we could. Okay. So then in that scenario, your opinion on the online learning it's very valuable. Okay, let us know how do you think about this transition to online learning and then how we can improve. Okay, so make sure you have your input over there as well. Okay. All right. So the next one I would try to finish as much lecture as possible today, and then there will be a little bit left for Monday. So in that case, on Monday, I probably will pre-recording lecture either today or tomorrow, and then provide a YouTube link on Moodle so you guys can start check on the last final lecture earlier. Okay, so that may give you some more time to work on your the last a few problems in the um, final homework assignment. Okay. So then on Monday, we don't meet at 9:10, but you can whenever you can watch the lecture at your schedule. Okay, that also give you some flexibility arrange the time to study for your finals. Okay. And last item here. So yesterday, as the department, we have decided lab assistant positions for different classes and different lab sections. As far as physics is concerned, there are still 4 positions, lab assistant TA positions available in the fall semester. Okay, in the spring semester, all 4 sections are filled. Okay. So if you are still interested in lab assistant physics, you can send me an email. Okay, anytime now or after the finals. Okay, or sometime in lab frame, but before next semester. Okay. So these 4 sections are physics 1 lab sections. We have general physics and university physics. Again, they are the same lab, so you guys should be able to do all of the 2 physics classes labs. Okay, so if you want, you can still let me know. Okay. All right. So we'll get started on the lecture part here. Oh, and then hope you sign up for physics lab and then also for chemistry, but we discussed yesterday. So it looks like the chemistry lab would need more help. So we decided to give you the chemistry lab assistant position. Okay, but if you are willing to do 2, because you indicated you just wanted to do 1 lab assistant. So if you still want to take the physics lab assistant position as well, you can still let me know. Okay. All right. So we'll get started on the lecture here. So last time we talked about imaging by mirror. So we start with plane mirror. So plane mirror, you will have the image being upright and then equal distance from the mirror as the object does. Okay, so you will have virtual image this time then. Okay. So although this is a plane mirror, but the mirror equation we checked last time also can apply here. Okay, so as one of the lab question asks, you can some of you guys have done that, so you see that, and then some of you guys will deal with this in the afternoon. Okay, and then we talked about last time. We also talked about spherical mirrors. So then this it's basically a curved mirror. Okay, depends on which side is being curved. If the inside is being curved, it's called concave mirror. If outside is mirrored, it's called the convex mirror. Okay, so in both scenarios, so because of the curvature, the part of the mirror you're looking at comparing to the whole sphere is very small. Okay, so then the distance the mirror will be like curved slightly. Okay, so then you can always draw from the center of curvature to the center of mirror. This is called principal axis on both scenarios. All right, and then if you have a convex mirror, all right, then or if you have a concave mirror, it's actually a divergent mirror. So then the parallel rays to the principal axis will actually reflect back. Okay, but they appear to be coming from the whole focal point. Okay, on the other hand, if you have a convex mirror, all right, let me see. I probably get it wrong. So for a concave mirror, sorry, it was a convex mirror earlier. So for a concave mirror, so then it's a convergent mirror. Okay, convex mirror is a divergent mirror. Concave mirror is a convergent mirror. So for concave mirror, if you have parallel rays to the principal axis, they will reflect and then go through focal point. Okay, so focal length for convex mirror, because it's a divergent mirror, so it's negative 1/2 of r. And then for a concave mirror, because it's convergent mirror, so it's positive 1/2 r. Okay, so the convergent mirror will have positive focal length, and then divergent mirror will have negative focal length. Okay. You can utilize 3 principal rays to find images produced by either a concave mirror or a convex mirror. Okay, so the parallel ray for a concave mirror, it reflects through the focal point. For a convex mirror, it appears to be coming from the focal point. Okay, the focal ray reflects parallel to the axis, the principal axis, and center of curvature ray reflects back along its incoming ray path. All right, so this is the 3 rays for concave mirror. So you can see basically you just need 2 principal rays to locate your image. Okay, but you could use the third one to double check. Okay, all right. So for convex mirror, you always get virtual image. All right, because the reflected rays, they do not intercept at any point, because it's divergent. Okay, it's a divergent mirror, so the rays come here will be diverged. The mirror equation we derived last time is simply 1 over distance, dO, which means distance of the object to mirror, plus 1 over di, which means the distance from the image to a mirror, equals to 1 over f. F will be focal length. Okay, this applies to both concave mirror and convex mirror. Okay. Imaging by the two mirrors, for convex mirror, it's always virtual image, it's upper right, reduced in size. For concave mirror, depends on the location of the object. So it could be, you could have real image, you could have virtual image. Okay, if you have real image, then it's inverted. If you have virtual image, it's upper right. Okay. Also, for magnification, which is defined as the size of the image divided by the size of the object. Okay, so the height of the image divided by the height of object, and then that's equal to minus the distance of image divided by the distance of the mirror, distance of image divided by the distance of the object. Okay. All right, so that's on mirror. On the lenses, so a lens is a vertical optical piece made out of a plastic material. Okay, so you can mirror, you can polish one side so it's nice curve. Okay, so depending on the curvature you have. Okay, so if you have convex curvature, then they are divergent convergent mirrors. Okay, in this case it's the other way around. If you have concave lenses, then they are divergent lenses. Okay. So for lenses, we will just focus on double convex and then double concave lenses in this class. Convex lenses, they are convergent lenses. Okay, so then parallel rays to the principal axis will meet at the local point. Okay, or focal point. For a concave lens, it's actually a divergent lens in this case. Then if you have parallel rays hit on one side, from the other side, when the rays come out, they will appear to be coming from the focal point. Okay. Similarly, you will be using three principal rays to locate the image formed by a lens. So a parallel ray, again, is a parallel to the principal axis. Okay, and then a focal ray that is either coming from the focal point or appears to be coming from the going to the focal point. Okay. Midpoint ray is the ray goes through the center of the lens. All right. So parallel ray will go through the focal point or appears to be coming from the focal point. Mid-ray range will just go right through. Okay, the lens not being deflected. Focal ray. Okay, it's going to be coming out of the other side of the lens and parallel to the principal axis. Okay. So image formed by thin lenses. If your focal length is positive, that means you have a convergent lens, which is the convex lens. Then you will have real image. It's going to be DI is going to be positive, and then the M is going to be negative. Okay. Yeah. In this case, also the distance of the object place and role here. So distance of object, if it's greater than focal length, then it's real. Okay, if it's less than focal length, then you will get virtual image. Okay. The third case is if f is negative, then it refers to the concave lens. So then you always get the virtual image. Okay. All right. Thin lens equations, you can also derive it by using similar triangles. So it's the same as the mirror equation. Okay, so 1 over dO plus 1 over di is equal to 1 over f. Okay, and then the magnification equation is the same. M should be equal to hi over ho, and then it should be equal to minus di over do. Okay, so some sign conventions here for lenses. Focal length should be positive for convergent lens. Okay, negative for divergent lens again. Magnification is positive for upright image, which means virtual image. Magnification is negative for invert image. Okay, so if you have invert image, then it's going to be negative. Okay, it's real image. Image distance is positive for real image, is negative for virtual image. Okay, and then DO is positive for real object, DO is negative for virtual object. So this is referring to if you have multiple lenses. Okay. All right, so we'll take a look the example on the lens here. So it says an object with a height of 2.54 centimeter is located 36.3 millimeter to the left of the lens with a focal length of 35. Okay, so focal length is positive. This means you have a converging lens, which is convex lens. Okay, so then it's asking you where the image is located. Okay, so you are looking for DI. You are given HI. You are given DO, which is the object's position to the lens. Okay, and then you are given a focal length. Okay, so you should be able to solve for the image location by using the lens equation. Okay, so on A, you are going to apply 1 over DO plus 1 over DI equals to 1 over F. All right, we are given DO 1 over 36.3 millimeter plus 1 over DI equals to 1 over 35.0 millimeter. Okay, so then you solve for DI. You will move this guy to the other side of the equation. 1 over DI is equal to 1 over 35 minus 1 over 36.3. All right, so then DI will be equal to, because this is 1 over that, so it will be equal to this guy minus this guy, and then you take the inverse of it. Okay, so this will turn out to be 977 millimeter. Okay, because your DO is very close to your F, the focal length. That's why you get very large DI. Okay, if you are very close to focal length, you get very large DI. Now, if you are at focal length, okay, you'll see that DI then will be infinity. Okay, because 1 over F should be plus 0. Then 1 over DI equal to 0. That means DI is equal to infinity large. Okay. All right, so this is part A here. Part B here, it says what's the height of the image. Okay, so you are given height of the object to be 2.54. Then you are looking for HI. Okay, so then you probably realize we will be using the magnification equation. Okay, so M equal to HI over HO. If we know M, then we can solve for HI because HO is known. Okay. Now M is also equal to minus DI over DO, right? So because we know DO, we know DI, DI is given, or we solve DI in part A, so then we can solve M in this case, okay? So that's equal to minus 977 over DO 36.3, okay? Then you can plug this into your calculator, get this number. I didn't do this. I actually set up that HI over HO equals to minus DI over DO, okay? So then HI should be equal to, you multiply both sides by HO, okay, minus DI over DO times HO, okay? So negative 977 over 36.3 times 2.54. This is in centimeter, okay? These two are in millimeter, so they will cancel out. You don't have to do the conversion. You can use the final answer in centimeter here, okay? So after you plug in everything into your calculator, you'll figure that this is going to be 68.4 in centimeter, okay? This is the height of the image, okay? That's what we are looking for. All right. So because you are very close to the focal length again, so then your image will be very large, okay? It's not going to be very far away, but very large in this case. All right. Any questions you guys might have, you can unmute yourself and then speak up, okay? Also, if you haven't sent a text in the chat, do that. I will take it as attendance later, okay? Okay, so if you guys have no questions, then let's move on here. So we'll briefly talk about chapter 26 here, all right? and then we should be able to move to chapter 27 today. All right. So chapter 26 about talks about vision, okay, and then optical instruments, okay. So basically, for vision, if we have problem with vision, then it's going to be most of the time, okay. So there's maybe other problems with eye vision, but very commonly it's if either someone is nearsighted or farsighted, okay. So for example, I am nearsighted, so I need a lens to correct my vision, okay. But let's take a look on a foresight scenario, because I'm getting old, so maybe sometime later I'll have this issue as well, okay. So um, for a far-sighted eye, it actually focus the object, okay, behind the retina, okay. So for a normal healthy eye, it should be able to focus the object right at the retina, okay. But because of this problem with the eye, so it's not doing that. So then we need a you can see the focal focus of is beyond the retina over here. So then we need to bring this guy to this, okay. So we need in this case, we need a divergent lens to bring this in front, okay, to be on the retina here. So then we need convex lenses, okay. So for reading glasses, it's convex lenses, okay. Now, for right now, what I'm wearing is the concave glasses because I'm nearsighted, so my eye couldn't focus the object onto the retina. It's in front of it, the image is in front of retina, so I need to bring this backward to be on the retina. So I need a concave lens, okay. All right. Now, you also realize that if the object, the same size of the object, if you are far away from the object, then you'll see the object will appear smaller. That's because this is the ray diagram here. You can see the image is going to be smaller if the object is going to be far away, okay? And then if the same size of the object is close to the eye, then the images will appear larger, okay? So that's what the object appears, the size of it when we see it, it depends on the distance to the eye, okay. Also, you guys use a lot of microscope. So in microscope, a couple of lenses is used. One is called objective lens, which is the lens close to the object, and then there's eyepiece, which is close to the eye, okay. So you use two convergent lenses, then you will be able to see the image being enlarged, okay, twice, okay. All right. So let's how much I wanted to talk about chapter 26, then let's move to 27, okay. So we might be able to finish 27 today, but there's chance we might not be able to do that, okay. If we couldn't do it, then I will put another short lecture video for the remainder of the chapter 27 for you guys to view earlier, okay, either today or tomorrow. All right. So chapter 27 talks about the wave optics, okay. So the wave aspect of the lights, okay. So let's take a look. So let's get started here. So if you guys like to play bubbles, or if you see bubbles, and then in the daytime, you probably see like this beautiful fringes forming on the surface of the bubble, okay. That's due to the interference of the wave, okay, of the light wave, because light is a wave. So then this is because interference of wave, then you see this interference patterns. Or if you happen to find a disc like this, CD disc or DVD disc, you'll see if you place this at a certain angle, you'll see again this colorful fringes forming. That's because on the surface of the disc here, there's a thin film, okay. So then when light reflects from the two surface of the film, the front surface and back surface, then they will interference, okay, that produce this colorful fringes, okay. So a little bit review on the wave. Okay, because light is a wave, then we can still use the quantities to describe wave here. So we can use the frequency, we can use the wavelength lambda. Okay, so the speed of light in vacuum, we can use c, that is 300 million meters per second. And then if it's in vacuum, we'll use v equal to c divided by m, index of refraction. Okay, so wavelength, then you can see in this case, because wave speed is equal to frequency times the wavelength. So then for a light to travel from one media to another media, actually its frequency will not change. Okay, but the wavelength changes. So then the velocity changes. Okay, so you can see in that scenario, so then the wavelength will change from if it propagate from one media to another. Okay, so in one media we will have one wavelength, in another media that wavelength will change a little bit. Okay, depending on index refraction, sometimes you can have wavelength changing quite dramatically. Okay, if n is very large. All right, and then a quick review on superposition and interference of the two waves. So if you have waves light waves coming from two location meet at same location, then there's interference or interaction of the two wave. Okay, so it's algebra sum of the two wave. Okay, functions. Now, if the two waves meet at one location, if their paths are different, then there's a path difference. Okay, due to path difference, then you will have interference due to that. Okay, we talked about this earlier, but this is based on mathematical addition of the two waves. Okay, so we are not going to go to detail because we just checked this on this one last week. Okay, so if the path difference is equal to, all right, let's see how to put this. Yeah, so if you do the two, okay, wave function add up, so then the difference, path difference will be delta x, okay, equal to x2 minus x1. Okay, if x2 minus x1, okay, we put it into delta x over here. Then if you do k times delta x, where k is 2 pi over lambda, then this is the difference in the sign function, okay, of the two in terms of phase difference. So we are basically kind of doing convert the path difference to the phase difference. Okay, so that's what you need to know. I think let me see. Okay, so yeah, in this y1 and y2 equation, you can see the difference is just k delta x. Okay, everything else being the same, but the difference is k times delta x. Okay, so then this is within this sign function. Okay, so then this is the phase difference of the two. If we translate the path difference into phase translation, then we can put it that way. Okay, so if this delta is equal to 2 pi times lambda times delta x, oh, I'm sorry, so because k is equal to 2 pi over lambda, so then delta is equal to 2 pi lambda times delta x. Okay, so we can rearrange the terms. We can do delta x divided by lambda, then times 2 pi. All right, so in this case, you can see if delta is multiples of pi, all right, then the difference is multiples of 2 pi. All right, so if that's the case, if the path difference is multiples of wavelengths, then you will get constructed interference from the two light wave. Okay, if the path difference is equal to half integers of lambda, multiples of lambda, then you are going to get distracted interference, because then this is going to be like the difference is going to be pi. Okay, odd multiples of pi, so pi, 3 pi, 5 pi, etc. Then you will get this distracted interference. Okay. All right, so now let's look at if you have, say, two slits here. All right, if you have a light shining on the two slits over here, So then you can draw two rays to be going through these two slits, okay? So, and then behind the two slits, if there's a screen here, okay, this, if you are doing the experiment like this, you'll see there's interference patterns form on this guy, on the screen over here. That's because now the light shining on these two slits, now coming from these two slits, there are two lights hitting on every spot of the screen over here, okay? So imagine one light coming from the left slit will hit over here, and then the second one from the second slit will hit over there as well. So then because you can see there's path difference, because the left light from the left slit will travel longer distance to arrive the screen on the left side here than the left light from the left slit over here. So that's path difference from the light coming in from the two slits, okay? So depending on the path difference, you will have sometimes have a bright image, bright spot here. That means construct interference. Sometimes you will have dark fringe over here. That means the destructive interference. Okay, so the pattern will alternating. You will have a bright fringe, dark, bright, etc. Okay. So let's take a look here. So this is what happens if you look at the wavefront. Okay, so sometimes for slit one, you'll have wavefront reaching the one point of the screen behind. Sometimes you have minimum reach that. So if that happens, then the two cancel out. Okay, so this is what you see on the figure C here. That's what you will see if you are shining a red laser through the two slits. Okay, you'll see on the center of the screen, where is the center of the two slits, you'll have more bright fringes here, and then as you go out from the center, you'll get weaker interference. That's because as light being diverted in the larger angle, intensity decreases. Okay. For the geometry of this, if you look at the path difference of the lights coming from the two slits, okay, in figure B here on the top over here, you can see, so S1, light coming from S1 will travel a shorter distance than light coming from S2, okay. Now, usually the screen is placed very far beyond the two slits compared to the slit width, okay, the separation of the two slits. So then the only difference would be the very small part of this, okay? So you can draw a line perpendicular to the lower parts over here. So then looking at this one, this is zooming into this region over here. So then the difference in paths 1 and 2 will be this small difference, okay? It will be equal to D times sine of the angle theta here. So D is the separation of the two slits, okay? Angle theta is this angle, is also this angle from the geometry. So then the delta x will be equal to D sine, okay? D sine is the delta x. So if we convert the delta x to be the phase difference, then we do delta x over lambda times 2 pi, because each lambda length is corresponding to 2 pi in the angle difference or phase difference, okay? So then delta equals to D sine theta divided by lambda, okay? So if this difference, phase difference, is equal to multiples of 2 pi, all right, then we can set up the D sine of theta over lambda times 2 pi equal to m times 2 pi. So the 2 pi and 2 pi will cancel out. Now, D sine theta sub m, okay, m just means which order of interference you are seeing, okay? It's counting from the center of the screen, which being 0 order, and then first order, second order, third order, okay? As you go further away from the center, you have higher order interference, okay? So just that simply just means the difference in phase is, say, in the center, because that's the center position, so there's no difference in the phase, okay, or no difference in the path, either way. And then the first order happens at about, if the phase difference due to path difference is 2 pi, okay, and then the second one is due to 2 times 2 pi, okay. So in this case, the 2 pi's cancel out, then the equation simplify as d sine theta equals to m lambda. Okay, m is m's order interference maximum. Okay, so that's where you see constructed interference when the data is equal to multiples of 2 pi. Okay. On the other hand, you'll see discharge interference when the phase difference is all the numbers of pi, okay, or the halves of 2 pi. So either way. So if that's the case, you set up d sine theta over lambda times 2 pi to be equal to 2m plus 1 times pi. Okay, so pi cancel out, then d sine theta in this case is m plus 1/2 lambda times lambda. Okay, so if you use this equation, then you are looking at interference minima or destructive interference. Okay, so there are two equations for double slit interference. Okay. Oops. All right, so let's take a look on this one here. Oh, I think I clicked too many times on the screen. This is the one we'll be looking at first. Okay, so this one says if you have two narrow slits separated by 1.20 millimeter are illuminated by lights that has 600 nanometer wavelength, and the interference pattern is viewed on a screen 2.5 meters away. Calculate the number of bright fringes per centimeter on the screen in the region near the center fringe. Okay. So let's take a look on this one here. Let's draw a picture here to represent the problem. Okay, so see actually what's being asked here. So you have two slits separated by 1.2 millimeter. So there's one slit here, one slit here. At a screen 2.5 meters away. So this drawing is not according to scale because 2.5 meters compared to 1.2 millimeter will be very large. Okay, but let's take a look here. So this is the center line. It's asking on the screen what would be the number of bright fringes per centimeter. Okay, so we can focus on the first centimeter away from the screen. So let's take this as 1 centimeter here. Again, this is not according to scale. Okay, but we'll see then this guy goes there, this guy goes there. Okay, so then the angle here theta. Okay, so this will be a very small amount. Okay, I didn't draw this in according to scale, but this one will be very short. Okay, so you can think about still imagine this is still 2.5 meters. Okay, if you imagine these two slits are very close to each other, then you're basically drawing it like that. Okay, or you can just draw the center line here. That will be the angle theta. Okay, so then when you arrive here, assuming this is a bright fringe, okay, so then we can apply d sine theta equals to m lambda. Okay, and then this will be the m's order bright interference. Okay, so if this is the m's order, then you have the number of orders bright fringes within 1 centimeter. Okay, so then that will give you the answer. Okay, so we are basically just solving on m, assuming this is 1 centimeter, this is 2.5 meters. All right, so we are given d, the separation of the two slits. Okay, we are given lambda, then the only thing we need is the theta here. Okay, but theta can be calculated using this geometry over here. So if this is theta, then you have 1 over 2.5 meters. Okay, at tangent theta. Okay, so your tangent theta then is equal to 1 centimeter divided by 2.5 meters. Okay, so we have to be careful about the two units here because they are not equal to each other. So you want to do conversion 0.01 divided by 2.5. Then they are both in meters. Okay. Now, when you see a problem with double slits, usually if this length is far, the screen is far beyond the two slits position, and then slits compared to this guy is smaller. So usually you can do small angle approximation. So for small angle approximation, it tells you the angle in radians. Okay, this should be in radians, not in degrees. Should be approximately equal to tangent of the angle, and then also approximately equal to sine of the tangent. Okay, or sine of theta. So you can use tangent theta as sine theta in this case. Okay, so now you can plug in all your numbers. 1.2 millimeter. All right. So let's convert it into meters. So times 10 to the -3. Okay, meters times sine will be equal to cosine or tangent. All right, equals to m times lambda. Let's also convert lambda into meters. Okay, so 600 nanometer, that means 600 times 10 to the -9 meters. Okay, then we solve for m. All right, and basically divide both sides by this. Okay, 600 times 10 to the -9 meters. All right, so that gives us I think 8.3. No, just 8. Sorry. So 8. So m equals to 8. All right, and then we are looking at 1 centimeter range. So that's the answer we needed. Okay, so it should be you should be able to see 8 bright fringes on this one. Okay. All right. Any questions you might have? All right, if not, then we'll move on here. So chapter 27, we are not going to go through each sections again. We'll just pick a few of them. All right. So the next one, we'll be looking at the single slit diffraction. Okay. So similar to double slit interference, if you have one single slit, narrow slit, if you shine light on it, you will see behind it on the screen, you'll see different patterns like dark fringes and bright fringes, etc. Okay, alternating. So this is because if you have a single slit, okay, so let's enlarge, let's zoom into the single slit here. You can actually divide the single slits to be small slits, okay? So you can divide it into very small openings, all right? Then for the opening on the top half here, any opening on the top half here, you can pick another opening that is half of the slit of the width of the slit, okay, in the bottom part. So then you can take those two openings as a double slit interference. So then when the light coming from this one and then coming from this one will reach on the screen at some point later, they will have diffraction pattern, okay, or interference there. All right, so and then you can do this for all of the different slits you divide into, okay, the smaller slits you divide into, okay. So in this case, then you'll be doing again d sine theta, which d now is, if you're looking at this one and this one, the separation of these two will be 1/2 of a, okay. That's going to be equal to, now if we are looking for the first, in this case, okay, we'll be looking at the first destructive interference, okay. That means we are looking for the location of the first dark fringe over here, all right. So that's the first one we are looking at here. So then you can see half and half will cancel out, then you come with this equation, a sine theta equal to lambda, okay. So in this case, this is referring to the first dark fringe, okay, or first minimum, all right. Again, you can use geometry to determine theta, okay. If you are told the location of the first dark image and then the length of the distance from the slit to the screen, you can do that with tangent theta. Usually, if the angle is small enough, you can also do small angle approximation, okay. If not, then we are not doing it. So for the angles to be small enough, it has to be less than 15 in degrees, okay. Just keep that in mind. All right, so general expression for them dark fringes for single slits, then it's a sine theta equals to m lambda. Okay, m is the mth order of the distracted interference length. Or in this case, we actually use diffraction. All right. So let's take a look here. The problem on single slit diffraction. So it says plain microwaves are instances on a thin metal sheet that has a long, narrow slit of 5 centimeters in it. The microwave radiation strikes the sheet at normal instance. The first diffraction maximum is observed at 37 degrees. Okay, so this is not small angle, but we can still use the single slit diffraction equation A sine theta. So equals to, in this case, it says the first diffraction minimum. So that means m equals to 1. Okay, theta 1 times that times 1 times lambda. Okay, so it tells us this this is 5 centimeters. It's asking you what's the wavelength. So it gives you this, and then you're solving for lambda. So it's pretty easy. Okay, quite straightforward. So 5.0 centimeter times sine of 37 degrees. That will give you the lambda. So then this will be 3 centimeters. Okay, equals to your lambda. All right. So for this one, it's quite simple here. All right. Any questions you guys might have before we move on? So if not, then we'll move on here. We'll check on the last topic of this class here. Okay, so last one deals about the interference, okay, of harmonic waves. Okay, so that means they are having the same amplitude, same wavelengths, same frequency. Okay, so K is wave number is associated with wavelength, and then omega is the angular frequency associated with frequency. Okay, if you have two harmonic waves, okay, and if they are differ in phase by delta, then you can actually, from mathematical, you can add the two wave functions up, all right, by using some trigonometry identity here, you arrive at this y1 plus y2 equals to 2a cosine theta over 2. Okay, so this is what we learned this earlier. So depending on the delta, you could have construct interference. Okay, that means the two add up. So then this delta has to be equal to 0 or multiples of 2 pi's. Okay, if the delta is equal to pi or 100 degrees, 180 degrees, then the two waves will cancel out. This is distracted interference. All right. And now also, if you have a wave, okay, and that goes, so for example, if you have a string made of two different materials from one part and then the other part, okay, so the first part is thinner material, the second part is thicker material. If you give it a wave, so it will travel into here. When it encounter the interface over here, so there will be transmitted wave, there will be reflected wave. Okay, so this is just like when the light hit on the surface, there will be reflected beam, there will be transmitted beam or transmitted ray, which is the refraction. Okay, so if the wave goes from thinner media to thicker media, then for the reflected wave, actually the phase will shift by 180 degrees. Okay, so if the maximum goes on the top here, it will return back as as minimum comes back. Okay, but on the other hand, if you go from thicker media to thinner media, then for the reflected beam, there is no phase change. Okay, so there's a 180 degree phase change here in the first scenario. There's no phase change on the second scenario. Okay. All right, and then that happens to the light as well. So let's take a look on this one here. So it says if light has a wavelength of 500 nanometer instance normally on a film of water 1.0 micrometer thick, what's the wavelength of the light in the water? Okay, so in this case, we'll see that the wavelength is equal to 500 nanometers. Okay, now if it goes into the water, water would have an index of refraction of 1.33. Okay, this is not given, but it's a constant that you can look up. Okay, so what's the wavelength in the water? So this is in air or in vacuum. Then in media, this should be reduced. So in media, we can write lambda sub m equal to lambda over m. So it's 500 nanometers divided by 1.33. Okay. So this then gives you 375 nanometers. Okay. B is asking you how many wavelengths are contained in the distance of 2t. The thickness t, okay, t should, yeah, the thickness of the water. Okay. So then how many waves contained here? You simply do 2t divided by lambda m, okay? So 2 times the thickness of 1.00, this is in micrometers. The wavelength is in nanometers. So you can convert micrometer into nanometer or nanometer into micrometer, either way, okay? So let's do this the other way around. So from micrometer to nanometer is 10 to the third, okay? Meters, then divided by, or nanometers, sorry, divided by 375 nanometers, okay? So this is 5.33. This many of wavelengths contained in the thickness of twice of the water film, all right? C is asking you, the film has air on both sides. What's the phase difference between the wave reflected from the front surface and then from the back surface in the region? Okay, so let's take a look here. If you have a thin film here, this is water, okay, and then the air here on top, air at bottom, water in between, okay. So the first ray light strike on here, it will be reflected one time, okay, and then part of it will be reflected down here, and then it will be reflected again, okay, for the first one and then second one, and then part of it will be reflected down, okay. So on the first one here, you are going from thinner media to thicker media. So then the reflect beam will have a phase change of pi or 180 degrees. Okay. And then for the second one, because you are going from water to air, you are going from thicker to thinner. So this one then no phase change. Okay. So the first ray will add 180 degree to it or pi to it. The second one will not. Okay. So then the difference between these two will be, the phase difference will be 180 degree or pi. Okay, either way. So then this reflector will have a phase difference of 180 degree or pi in that scenario. Okay. Because you are reflected from, you are going from thinner media to thicker media, there's a phase change. If you are going on the other way around, you don't have it. Okay. All right, so this is this one here. Any questions you guys might have? If not, then we are be looking at the thin film interference. So this is where if you have a bubble, you'll see on the surface of it, there's this colorful interference. That's because there's a thin film over here, so like water film. So then there's first reflecting from front surface, and then the second reflecting from the back surface. When the two reflect rays meet at your eyeball, then there's interference happening over there. Okay, so then you see that. Okay, so this is what happens. Okay, so this is the thin film with a thickness of t. So the first reflected ray will have phase change, and then on the second ray, okay, now it depends on what's below here. If there's water below here, or yeah, it depends on N1, N2, N3. Okay, so if N1 is less than N2, less than N3, so the first one will have phase change 180 degree or pi. The second one will also have that, okay, because this is thinner compared to this guy, okay. So then when the two arrive at your eye, they will not have additional path difference, the phase difference, okay, because that will be the same. Now, for N3 minus N2, or if the other way around, if N3 is less than N2, okay, then the two will have 180 degree phase difference, okay. So this is the solely due to path difference, okay. You are going to examine if N1 less than N2 less than N3. If that's the case, then you don't add 180 degree or pi to it. You don't add pi to it, okay? If your N3 is less than N2, then you'll add pi to it to the phase difference, okay? So the phase difference, okay, there are two parts of it here. One part is due to path difference, okay, which is delta x over lambda times 2 pi. Another one is depending on if there's a phase change, okay. If there is, for both of them, they cancel out. If just for one of them, then you want to add pi to the delta, okay. So these are the two scenarios, okay. So if there's just one phase change for one ray, reflected ray, then you add it, okay? If for both rays, then you don't add it, okay? So you have to examine the scenario very carefully, okay? So if you guys are in the biology lab, sometimes you can pick up a slide, glass slide, then or two of them. So you put, say, a very thin piece of paper here. So then you make an air gap there between the two slides. So then this can be treated as air thin film. So then when the two lights reflect light from here and then here arrive at your eye, you might see this pattern over here. Okay, you can try that later sometime in the biology lab. Okay, so it looks like we are just going to run a couple of minutes over for the last example here. So let's do that. Okay, if you have to go, you can free to go after 10:10, but if you can stay, that would be better. Okay, so I'm going to run a little bit over time today, but then that will do it for this class. Okay, we don't have to meet again, or I don't have to make another video for the last lecture, because this then is the last slide of the class. Okay, so this one says a thin film of oil that has an index of refraction of 1.45 rests on an optical flat piece of glass with an index of refraction of 1.60. When illuminated by white light at normal instance, light of wavelength 690 and then 406 nanometers is predominant in the reflected light. Okay, determine the thickness of the oil film. Okay, so let's draw a figure here. So this thin film of oil. So this is oil here. Okay, it's resting on an optical flat piece. Okay, so this is optical flat piece over here. Let's assuming this is a glass, okay, or whatever. Like yeah, it says glass. So there will be air on top of that. Okay, so N1 we can take at 1. Okay, the index of air, or you can take 1.0003. It's up to you, but I will take 1 here. The thin film N2 is 1.45. Yeah. And then the glass is 1.60. Okay, so these are indexes of refractions for the three materials. Now we can see if there's a light strike on this one. Okay, so the first will be reflected on the air oil interface. So this is ray 1, and then refracted, and then hits the back of the thin film oil. It will be refracted again. Okay, so then this is ray 2. Okay, for ray 1, it's going from thinner media of air to oil and then reflected. So then there's a pi change in phase here. Now for the second one here, you are going from N2 1.25 to N3 1.6. You're also going from thinner media to thicker media, okay, thinner to thicker. So then for the ray 2, it also will have a phase change of pi. So let's do plus pi, okay. So then the two has both have plus pi, so they will cancel out in the for the phase difference, okay. So overall phase difference, one part is coming from 2t, the thickness of the film divided by lambda in the film, okay, times 2 pi. This is due to path difference. Okay, plus due to phase change, the second part, due to phase changes. Okay, for the first ray, there's a pi phase change. For the second ray, there's also a pi phase change. So the two will cancel out. Okay, so basically this will be 0. Okay, so then this is the overall phase difference due to path difference plus due to phase changes. Okay, so you can see this is a scenario. Now we are looking for predominant light. So that means we are looking for the constructed interference. So this add to be equal to, for constructed interference, it should be 2 pi times lambda. Okay, so delta equal to that. Okay, to be constructive for constructive interference. All right, so you can set up 2t over lambda n times 2 pi equals to 2m times pi. So 2 pi cancel out. So 2t equals to m, or 2t equals to m times lambda n. Or let me just, sorry. Let me just keep that here. 2t over lambda n equals to m, okay? Now, lambda n is equal to lambda divided by n, okay? Because we need to use wavelength in the media, okay? So that's equal to wavelength in water divided by n, okay? Or in the air divided by n. So then this one becomes, if you plug this guy into here, it becomes 2m times t over lambda equals to m, okay? So for the two wavelengths of 690 and then 460, they are constructed interference. We can apply this equation to the both wavelengths, okay? So for the first one, you will have 2 times 1.45. So the media we're looking at is oil as the N2, okay? So the second media here, because that's where the path difference is due to. Times the T, thickness T, okay, divided by 690 for the first wavelength, that equals to m. Okay, so you have first equation. You are going to apply this to the second light. Okay, 1.45 times t divided by 460 nanometer. All right, that equals to, all right, because this is 690, this is 460. So then the right hand side should be less than the right hand side in the first equation, right? Because you have, or it's larger. So if you have smaller, larger denominator here, you have smaller on the result. So this should be m plus 1, okay? Because you are going to have integer orders of interference. So if this is m's order, then the next one should be m plus 1, okay? So this is 2. The 2, okay? So you're going to set that up, okay? So when you have a problem like this, you are going to do it that way, okay? So set this up. So you have two equations. You have two knowns, okay? Then you can solve for the 2. You can do this divide by that, equation 1 divided by equation 2, which means left hand side of equation 1 divided by left hand side equation 1. So basically 2 times 1.45 times t, and this will cancel out. So you'll have 460 divided by 690, okay? Nanometers equals to m divided by m plus 1, all right? So you're going to solve it this because this is 2 times of 230, but this is 3 times of 230. Okay, so then you can see m is going to be equal to 2. All right, now you can plug m equal to 2 back there. You can solve for your t. Your t is going to be 476 nanometers. Okay, so you have solved both for the number, the orders of interference for the 690 nanometer wavelengths. You also solve for the thickness of the thin film. Okay. Any questions you guys may have on this one? All right, if you don't have questions, then we'll stop here. Okay, we will not meet on Monday. Okay, this is the last lecture we'll have. Okay, so you can use the time you have on Monday to either work on the homework problem or solve or study for your other exams. Okay, so yeah, thank you so much for you guys to spend the whole year with me. I really appreciate it. I had a great time with you guys. Unfortunately, we couldn't have the labs for the last 4 labs in physical lab, but we were able to meet virtually. Okay, thank you again so much. Okay, good luck on all your exams. So I will be still available for questions if you want. We can set up on the Zoom office hours one by one, one-on-one meeting there. Okay, so just let me know if you want it. All right. Otherwise, see you guys later. Okay. Goodbye.